The first half of lesson 7.5, we're going to focus on the zero product property, which is going to set up what we need to start solving polynomials. You may have noticed that we've done a lot of operations with polynomials. After classifying them, we added, we subtracted, we multiplied, but we haven't actually solved them. We hadn't really started the work of solving for x and what values of x make that polynomial true. So that is what we're going to dive into in this second half, and the zero product property is going to be an integral part of us being able to solve polynomials. So let's talk about, before we actually talk about the zero product property, let's just do a little review, because it's really a concept that you are probably very familiar and it's going to make a lot of sense to you. It's something that you already know to be true. And that is essentially that anytime we multiply by zero, it doesn't matter if you just have two things, you might have three things being multiplied, but if at any given point you're multiplying by a zero, the answer to that is automatically going to be zero. So this is just a side example. It doesn't matter if the number you're multiplying is positive or negative or even a decimal. You could just take about anything and multiply it by zero, and your answer is always going to be zero. Okay, that's always true. The other really important thing to remember is that if we multiply two things that are not zero, we'll never get a zero. That's kind of the other side of that coin, right? So we know if we multiply by zero, we'll get a zero. Okay, but more importantly, if I have two numbers that I multiply together and neither one of them is zero, then that answer is never going to be zero. Okay. If one of these is not a zero, there's no way you can get zero as a product unless you are multiplying by a zero on one of your numbers. Okay. Now, again, this is something that's probably very intuitive. You know that to be true, even if you hadn't formally, discussed it as the zero product property, but that's really at the heart of that. All right. That when we multiply by zero, we get zero. And then in fact, that's the only way we can get a zero in multiplication. We cannot multiply a positive and a negative or a 1/2 and a 2. There's no other way of multiplying and getting zero unless one of them is zero. Okay, so pretty intuitive situation there. That is going to be at the heart of how we solve polynomials. Okay, our goal in general is going to be to set the polynomial equal to zero and then write it as the product of two things. Okay, that's going to happen through what we call factored form, and that's what we're going to talk about for a little bit here. Okay, if we can set a polynomial like this guy, maybe equal to zero, and then rewrite it in factored form so it is the product of two things, then we'll be able to use the zero product property to solve. Okay, so that's our game plan. Okay, for that, we're going to learn throughout this half of the unit here, this half of this chapter in this new unit, how to take things that are in standard form and sort of go in the opposite direction than we did in this previous unit. In the previous unit, we practiced multiplying. So we knew we could distribute x and get that answer, or we could FOIL here and get this answer. For these purposes of solving, we're actually going to practice going in the opposite direction here and taking something that is originally in that standard, nice, cleaned up form and rewriting it in that separated, factored out form, meaning as two separate things being multiplied. Now, why on earth would we want to kind of break this down and rewrite it like this? Because then later our goal will be then to set it equal to zero and use a zero product property to solve. So that's the game plan. Okay, so just to do a little quick definition of what exactly it means, a polynomial is considered to be in factored form when it is written as a product of factors. So we're going to do the reverse, like I said, of what we practiced in the first half of the unit. Like I said, we were getting a polynomial, a 2x2, and we were doing box method or FOIL or distribution to get it to look like this. Now we are going to probably start off with things being given to us in standard form, and we're going to work this direction to rewrite it as the product of two quantities. Okay, now when one side of an equation of a polynomial is in that factored form, and then the other side is equal to 0, then we can use the zero product property, as we just discussed. So the zero product property. Okay, to solve that equation. Okay, and when we solve it, the solutions are basically the equations are the x values that make it true. So if we're able to set it up as the factor or the product of two factors equal to 0, and then find the x's, those are basically the x's going to make the original polynomial true. So the solutions of a polynomial equation are also sometimes called the roots. So you might hear me say that, and I mean the same thing. Or sometimes we also call it the zeros. So there's a lot of words for the same thing. I know that can be a little weird, but we call it the solutions, we call them the zeros, we call them the roots. That all basically means the x values that make that polynomial true, or that polynomial equation true. And that's what we're going to be working on practicing. Sometimes you're going to have a polynomial that has two roots that are the same number, or two solutions that are the same. And that is called a repeated root. Remember, if I write it down, you write it down. Okay? And so this is just kind of laying some groundwork of vocabulary so that we can begin. So again, the zero product property, I already kind of described it, we're just summarizing it here, is basically states that if the product of two real numbers is 0, then at least one of them must be 0. Okay, very fundamental, easy concept. But it's exactly what we're going to use to solve these polynomial equations. So now our polynomials are actually going to include equal signs, and then they're going to be equal to something. And our goal will always be for it to be equal to 0. So we'll later on, as the days go by here, we'll talk about how we're going to make that happen if it didn't already come that way. Okay, but our goal will be to set it equal to 0, and then on the other side have it in factored form as a product of two smaller polynomials. Like in this case, I have a monomial 2x and a binomial x minus 4. So the product of those two is giving me 0. And then I can use the zero product property. I can say, well, the only way that this and this multiplied together can give a 0 is if the first term is 0. And so we kind of make these little mini equations. We say, okay, well, one option is that this guy would have been the one that was 0. So 2x equals 0. We divide both sides by 2 to get x by itself. We solve that little mini equation. 0 divided by 2 is still 0. So this is a solution to that polynomial right there. But there's also the possibility that perhaps this one was the one that was 0. And so we could set that binomial x minus 4 equal to 0 also, and then solve that by adding 4 on both sides. We cancel here, and then x would have to be 4. So both of these, and this is really common for polynomials to have multiple roots or solutions, okay? Both of these are solutions to that polynomial, because if I plug in a 0 here, and I work the math out, you're going to see that it makes this equation true. And if I plug in a 4 here, and do the math, you're going to see that it makes this equation true. Okay, so that's how we use the zero product property combined with the factored form of a polynomial. Okay, same thing here. If I have this binomial times that binomial equals 0, the only way the product of these two things can possibly be 0 is if either the first one is 0 or that guy over there is 0. Right, those are the two options. So you set each one equal to 0 in a little mini equation, and you solve them. So let's try a couple of examples. Okay, let's start here with number 1, just nice and simple. The main things that you want to check for, which I think for the most part will be true in this first introductory lesson, is that one side is written as the product of two factors. Okay, either a monomial and a binomial. Sometimes it'll be two binomials. Sometimes it might be, 3, but it's all being multiplied together, and that it's equal to 0. Those are the two requirements there. Okay, and in this case, I have that already. So it's telling me here that x times this x plus 5 is equal to 0. The product of these two things can only be 0 if one of or the other is 0. So the only way this can be true is if x, that first term here, that monomial, is equal to 0, or if this binomial x plus 5 were equal to 0. So you kind of set two little mini equations and you solve them, and whatever they give you, those are the solutions to the original. Okay, and so let's try it. Well, this was already pretty much solved. So this is telling me that x equals 0 should be one of our roots or zeros or solutions. And for this one, I do have to do a little bit of work. I need to subtract the 5, move it to the other side, get x alone, and then this one's telling me that x could also be -5 as a solution. Okay, let's test that. Let's see if that makes sense. So what I'm proposing, according to my work, is if I plug in a 0 here and here, it's going to make that equation true. So let's find out. I'm going to put a 0 in where the x was, outside and inside. So the two x's are replaced. And the question is that still equal? Does it make it true? Right? Well, let's find out. 0 plus 5 is still 5. So I end up with 0 times 5 here, which is indeed 0. 0 times 5 is 0. That works. Okay. Let's try the -5 and test that one. So if we use a -5 where the x's were, so I would put a -5 here, parentheses, a -5 again, plus 5. And according to me, right, this should equal 0. Let's find out. Well, parentheses first, -5 and a +5 is 0. And then I have this -5 on the outside, but -5 times 0 is still 0. So yeah, this worked, and indeed it did make both. And if you tried plugging anything else in, you're going to see it doesn't work. These are the only two values of x that make that original equation true. It's 0 or -5. Those are the two things that work. Okay, let's try one more that is like this with a monomial times a binomial. It's written as the product of those two polynomials equal to 0, so we're okay there. So we'll take this front monomial and equal to 0, and we'll take the p minus 2 and set it equal to 0. Okay, and then we just solve each one. So here I divide by 5 to cancel on the left. P equals 0 divided by 5, which is still 0. Okay, and the other solution is p minus 2 is 0, so if I add 2 on both sides here, p equals 0 plus 2, which is just 2. So these are the two zeros or solutions to that polynomial equation. P can be 0 or it can be 2. And again, very easy to plug in and check to make sure you did it right. All right, let's try one that is a binomial times a binomial. Let's try this one here in the middle, number 5. Again, as long as it is the product of two factors, two binomials here, and it's equal to 0, we can use the zero product property. So right now I have that this binomial times that equals 0. So I'm going to take each individual one, set it equal to 0. Okay, so one option is that this 2b minus 6 would have resulted in a 0, or the other option is that 3b plus 18 would have resulted in the 0. And then you just solve each one of these as its own little separate equation. So to get b alone here, I have to add 6. This is all solving 1- and 2-step equations in the fall and in previous years. 0 plus 6 is 6, but then we still have to get rid of the 2, so this is a 2-step equation, and I find out that b would have to be 3. If b is 3, then all of that will be 0, and when I multiply by that 0, it would make this true. So that is one of my roots or solutions right here. The other option is this guy, so let's solve it. We'll move the 18, do the opposite, cancel it on the left. I still have 3b. 0 minus 18 is negative 18. Second step is to get rid of the 3, so we'll divide. Opposite of multiplying is dividing to cancel that. And b ends up being negative 18 divided by 3, which is a negative 6. So this is our other solution or root. Okay, both of these, if we plug them in, will work. Okay, if I make a 3 here and here, it's going to make this true, and if I make a negative, and if I insert a negative 6 here and here and test it, it's going to make it true. And nothing else other than those is going to work. Okay, all right, let's move on to number 7. So on number 7, we've got a little exponent up there, and this is squared. So that means that that root is repeating. It's the same, it's times itself. So that's the first thing I want to remind you. And I think that as you're working these, it helps and it pays off to go ahead and expand that. So if I see w plus 4 squared, I want to remember that really means that I have a w plus 4 factor and then another w plus 4 factor. And then I have that w plus 1. So that means that I'm really multiplying 3 things together. 2 of these and 1 of those, right? So there's 3 things here. And there should be, 3 different solutions. Now, a couple might repeat. You might start to realize, well, it's going to be the same. And you're right. That's called that repeated root that we talked about on our front page vocabulary. That's what we were referring to. This is when that repeated root is going to happen. We know that it's going to, but it's important to note it. Okay, it actually does make a little bit of a difference in terms of the graph. Not so much on the solutions, but of graphs, which you will talk about later. Okay, so if this times this equals 0, once again, the only way that's can be true is if one of those factors is 0. So we'll set each one here equal to 0, or it could be this one equal to 0, or it could be this one equal to 0. And we kind of just solve each one, right? So w plus 4 equals 0. If I solve that for w, I would have to subtract that 4, and I would get w equals -4. Now, you could definitely show the work, but the problem, you can probably start to realize, oh, well, the same exact thing is going to happen here. Since they're exactly the same binomial, when I solve it, I'm still going to get another -4 there, okay? So that's called a repeated root. Okay, so we can now say, oh, one of the answers is -4, and you can say this is a repeated root. And on the graph, it would actually do something pretty cool there. And we'll, like I said, we'll talk about that soon. And then the other option is this w plus 1. Don't forget about that one. We have to solve them all. And so w would also be -1. That's not a repeated root. That only came up one time. Okay. And so that's a regular, just single root right there. Okay. So we've got -1 as a solution and -4 as a solution. But I just want to make a note that that -4 is a repeated root. Okay. All right, I'm going to finish off with number 9 here, and then we'll try a couple word problems before we wrap it up. So if we check out number 9, we have now, these are, look, at least for now, appear to be definitely different binomials. They appear to be anyway. So I want to make sure I consider all of them. This times this is 0, only if one of those, any one of those being 0 would make this true. So if this were 0, it would make that true. So we've got 4 minus m equals 0. So I have the scenario where this middle one is equal to 0. And we have the scenario where that -2 minus 3m is equal to 0. Okay. So let's tackle each one of those. Okay. So to get this alone, we would want to move that 4 to the other side with a negative and cancel it from the left. Don't forget that negative though. That leaves me a -m. So I'm not quite done after doing that. Okay. Then I would want to fix this. So that'd be easy enough just to multiply or divide through by a -1, which changes our signs, but that would fix that sign issue there and make my m positive. So m would equal -4 over -1, or in other words, a positive 4. So there is one of our roots. Okay. Let's try this guy in the center. We want to get m alone, so we'll start by moving the 8, getting rid of the 8 on the left there with the opposite. That cancels. And we have 2 over 3m ends up being that -8. And then when we're multiplying by a fraction, just a little reminder, it's been a while, I know. The easiest way to think of it is to multiply by the reciprocal on both sides. That's the easiest way to think about it. Multiply by the reciprocal on both sides, and that cancels the fraction completely on the left, because 3 over 3 cancels, 2 over 2 cancels, and we're left with just m. And on the right, this is pretty simple to do. You multiply by the top, divide by the bottom. So -8 times 3 is -24, and -24 divided by 2 is -12. So there's the second root. Okay. And then when we do this last one, we'll move the 2 first. Always move what is adding or subtracting first. That leaves us with a negative 3m is equal to 2 here, because 0 plus 2 is 2. And then we'll divide both sides by that negative 3. Canceling both the 3 and the sign, and that leaves us with m equals, and you know that doesn't go in evenly, so that's okay. It's a fraction and no problems with that. So this has 3 genuinely different roots here. Your solutions are 4, negative 12, and negative 2/3. Every one of these would make that top polynomial true, and therefore they're all solutions or roots or zeros. Okay, so that's a zero product property in action. And what we're going to work on really after that going forward is getting things to set up this way, right? But for today, this is going to be our practice, just getting really comfortable with a factored form of a polynomial equal to 0 and using the zero product property. All right, let's finish out here with a couple word problems. Let's look at number 10. It says the front of a storage bunker can be modeled by this equation. You've got a constant here, and then a binomial, and then a binomial. And they're all being multiplied. So this is what we call factored form. It's just written as this times this times this, where x and y are measured in inches. The x-axis represents the ground. Okay, so we want to find the width of the bunker at floor level. Okay, so we want this distance right in here, like from here where the bunker hits the ground and here, what is this total distance? That's what we're looking for. Okay, just to kind of set it out for you. So what we want to do in this kind of problem is we want to use the zero product property. Okay, so let's write that down. Use, since these are our nodes, the zero product property. Okay, to solve for x. Okay, when y is 0. Okay, and here's why. Because on a graph, remember our output is 0. That's like instead of y equals, we're making it 0 equals. So why would we want to solve for this x when y is 0? That's what we're doing. Well, think about it. On a graph, when equals 0, I am on the x-axis. Okay, so on the x-axis, that is the horizontal line where y is equal to 0. Okay, y is equal to 0 along this x-axis. Right. And then, you know, above it is the positives, below it is the negatives, but the vertical line y equals 0 is the x-axis. So if I want to know this location and that location, then I'm asking basically what is this x-coordinate and this x-coordinate when you are at y equals 0. Okay, that's really leading us into understanding that all of these solutions are basically the x-intercepts of your graph. And we've talked a little bit about that in linears, that we would a lot of times call the x-intercept the 0 of the function. You're starting to probably see here why. Okay, all right, so what we want to do, that is where it's going to hit the ground, where y is 0, and we want to know those x values. So we're going to take this lovely equation, negative 5, 2, 1, 6, and then in parentheses x minus 72 and x plus 72, and we want to set that equal to 0. Okay, now here's another neat aspect about the zero product property for you to keep in mind. We have talked a lot about how the only way that things can multiply to give you 0 is if one of them is 0. Okay, here's another cool fact that you, I'm sure, know. Okay, is that the only thing that's going to make this be 0 is whichever one is a 0. I'm saying that word so much today, right? But here's my point. If I have, for example, 3 times 0 is 0, there's no way that this is what caused the 0, right? So if I already know one of my numbers is like an actual non-zero value, there's no way that's what caused it, okay, to be 0. It would have to be, you know, something else that is equal to 0. So here's my point. This first term is a constant. There's no variable here. Is there any way that negative 5 over 216 can make this whole thing go to 0? No, because it's not 0 and it doesn't have a variable that could make it be 0. So it wouldn't make any sense for me to take a number that I already know isn't a 0 and doesn't have a variable and try to set it equal to that. Doesn't that look weird already? That's like me saying, hey, I think 7 might be equal to 0. That doesn't make sense, right? So if one of your factors is just a constant, it doesn't have a variable, okay, it's just a non-zero constant, then you don't have to worry about using the zero product property with it because it's not going to make sense. This is never going to be true, okay? It's got to be one of these other ones that has a variable that could cause it to be 0, okay? So if it's a constant with no variable, that's never going to be the culprit or the reason why this whole thing is 0. This is never going to make it, it doesn't even have an x value for us to solve for either, right? So I really only need to worry about this guy and this guy, these other two factors that do contain my variables. Okay, so I'll set this guy equal to 0, and we'll add 72 on both sides. That means x equals 0 plus 72, which is just 72. And then I'll set this guy equal to 0 over here. X plus 72 equals 0. And to solve that, we'll subtract. Okay. And that gives me x equals negative 72. Okay. So these are the x-intercepts, or the locations where our bunker hits the ground. Now be careful, those are not necessarily our answer. This is a word problem. It goes beyond just finding x. It wants to know the width of the bunker. Okay, and so, but what we do now have is a location. We know that it has an x-intercept or an x-coordinate here of 72, and then over here it enters back to the ground at positive 72. I want to know the total distance. So you got to remember, distance is like from, how far is one number from the other. So I really actually want the difference of these. If you say it's 72, then you're only going from like 0 to 72 to the right or to the left, but it's not the total distance. My total distance is how far is negative 72 from positive 72. How far are they away, right? Well, distance is really just finding the difference between them, right? Sorry, let me rewrite that. So that's positive 72 minus that negative, right? And that double negative becomes a positive. So we know that's really 144. If we go all the way from negative 72 to positive 72, that's basically 72 feet here on the left side, on that half, and another 72 on the right. You basically add them together. So our final answer here is that the width of this bunker is 144 feet. Okay, that's how wide it must be. Okay, so just to piggyback on that, we're going to do number 11 in class together. Okay, it's very similar. If you actually want to check it out, you can. And then the culminating thing here is, graphically speaking, when you find these zeros, these roots, these solutions, okay, we want to basically set it equal to 0, and what we will be finding will be those x-intercepts. We'll be finding this ordered pair, that ordered pair. So on a graph, okay, the x-coordinates or x-intercepts, okay, write this down, this is important. The x-intercepts on the graph are the solution, are what we consider the solution of a polynomial equation. Okay, that's a big idea. Okay, so we'll finish off here with number 12. If we've got something like this guy right here, and I want to find the x-coordinates, again, I want to remember that the x-coordinates where the graph crosses the x-axis, in other words, the x-intercepts, are happening at the x-axis where y is always equal to 0 there. on the x-axis, the y-ordered pair or coordinate is always a 0 there. So the reality is we're taking that equation that's at the top there, x minus 11, x plus 6, and we want to know when does it equal a y value of 0? When is it here on the, if we set it equal to 0, we're setting it here where it hits the x-axis. And whatever those values of x are, that is going to reveal to us what those x-intercepts are. And those are the solutions. They're also the zeros or the roots. Okay, so we'll do this one last time. As long as you know that for the x-coordinates where it crosses the x-axis, or in other words, the x-intercepts, you're still just setting it equal, then you realize it's still the same kind of problem. We just want to know when is this right here equal to 0, and when is this equal to 0. And if we solve that by adding 11 on both sides, we realize one of those x-intercepts must be at 11. Does this look like it could be? Yeah, this is going by 4, 8, 12. That looks like 11. Seems very reasonable. And over here, negative 6 on both sides. So we move it. 0 minus 6 is still a negative 6. So 4, and then about halfway between that is 8. Yep, that looks very much like where this is hitting indeed. These are the zeros, solutions, or roots. And graphically speaking, they are the x-intercepts of your graph. Okay, so try 13, and then we'll do number 11 together in class.